This is for chapter 26, and this is part 2. We're going to start off in your notes where we left off talking about the anatomy of a nephron. And this is the glomerulus with this blood capillary network that filters the blood that we talked about, and this is the Bowman's capsule around it that receives that filtrate. Remember that the blood vessel that brings blood to this glomerulus is the efferent arteriole, and the blood vessel that leaves this glomerulus is the efferent arteriole. So this is unique in the fact that it's an arteriole, a capillary, and then another arteriole, because usually it would be a venule. Blood coming into the efferent arteriole is under very high pressure. Notice that the efferent arteriole has a larger diameter than the efferent arteriole. So blood's coming in here under high pressure, and these pressures, essentially that pressure is going to overpower the other pressures in this glomerular capsule to push the filtrate out, and we'll talk about that. Also remember here is the ascending limb of the nephron loop. That's right next to this area, and we have cells on the ascending loop called the macula densa that are right next to these cells of the efferent arteriole, and together they form what's called the juxtamedullary apparatus that helps to regulate blood pressure. So for chapter 26, we're going to talk about the 3 basic functions of a nephron and the collecting ducts. Yes, they form urine, but how do they do it? These are the 3 steps. And we'll talk a little bit later about the details of how to make dilute or concentrated urine. So right now we're not going to dive into all of those details. We're just going to talk a lot about it generally for the most part. So the first step is glomerular filtration. This is what I just talked about, how the force of the blood coming through filters the blood, the waste-laden blood, out of the blood and into the nephron. And that's referred to as the glomerular filtration rate. It's the amount of formed in the filtrate on the renal corpuscles each minute. After glomerular filtration, we have tubular reabsorption. So some of that filtrate that just went into the nephron returns back into the body, to the blood and tissues around it. The third step is tubular secretion, the opposite of tubular reabsorption, where waste goes from the body, the blood, back into the nephron to the final product of urine. So first, glomerular filtration. Protein fill filtrate. So essentially, blood's coming in through the glomerulus, and most of the blood goes into the nephron, except big proteins. So we're talking ions, we're talking glucose, we're talking water. Plasma, protein exit cellular elements, so not big proteins, and it exits the renal corpuscle via the efferent arteriole, yes. Okay, so blood comes in, filters it out. So this is a great image to refer to when we're talking about the 3 steps, if you just want to get the gist. So here is the efferent arteriole, and it's going into the glomerulus, leaving via the efferent arteriole. This is the capsule. This is filtration, this first arrow. The second arrow is reabsorption from the nephron into the blood, and the third arrow is secretion from the blood back into the nephron, and then the eventual product is urine. So actually most of the fluid that is filtered, most of it is filtered, but we can't afford, and we don't have the time to excrete that much fluid, so most of it is reabsorbed. This chart is a great to refer to, and your book also has it, but it shows in the plasma, so actually in the blood fluid, what is the amount of water, protein, glucose, urea, and creatinine, which is a byproduct of muscles working, amount that goes into the filtrate. So of the 3 liters of fluid in your plasma, 180 liters is filtered into the filtrate per day. That's a lot. But look at how much is returned to the blood via reabsorption. Most of it. So the amount of urine that you actually excrete after secretion per day is about 1 to 2 liters. We can also see another good one to look at is glucose. 3 grams in plasma, 162 grams in the filtrate per day. And we reabsorb all of it. So you shouldn't have any glucose under normal conditions in your urine. So that's pretty cool. So filtration, the push to filter that fluid from the blood into the nephron is opposed by two other pressures, hydrostatic pressures, and that's two opposing forces. They're called Starling forces. One of them is blood hydrostatic pressure. Wait, no, that's the main one that I just talked about. The force of the blood pushing out the fluid from the blood into the nephron. And it's about 55 milligrams of mercury. And it promotes filtration. The opposing forces, one of them is capsular hydrostatic pressure. As fluid moves from the blood vessels into the capsule around it, there's actually a pressure that's pushed by the fluid that's already in the capsule back on the capillaries. That's what that is, and it's about 15 millimeters of mercury. Another force that's opposing filtration is blood osmotic pressure, and it's about 30. 30 plus 15 is 45, opposing. Remember, the positive push is 55. So 55 minus 45 is a positive 10, and that's going to be important. So that's just the pressure of the proteins that are actually in the blood here, pulling. Oops, I gotta get my visual here. The pressure of the proteins preventing fluid from moving out, opposing filtration. So how do we calculate net filtration? That blood hydrostatic pressure, which is 55, minus the blood osmotic pressure, which is 30, minus the capsular hydrostatic pressure, which is about 15, for total net filtration, 10 milligrams of mercury. So this is just showing all the numbers what I just said about. 55 is the blood hydrostatic pressure, and these purple and blue arrows represent the opposing pressures that are trying to keep essentially that fluid in there. Remember we talked about how the actual anatomy of that blood vessel, how it's fenestrated, has these larger holes that allow ions, glucose to easily pass through from the blood into the nephron. But it does prevent larger proteins from going through. This is the video that you're going to watch to fill out a worksheet. And again, a closer view at the pressures. So once in this picture, this blue arrow, this white arrow are overcome, now we have the net filtration pressure, and this is the urine that's going to travel down the nephron. So we're here. We're just to here right now. We've done glomerular filtration. The next step is tubular reabsorption. And this is a great image to refer to. So we're talking about substances moving from the nephron back into the blood. Now, this happens all along the rest of the nephron. So after we leave here, we're talking about the proximal convoluted tubule. We're talking about the loop of Henle, the distal convoluted tubule. Tubular reabsorption happens throughout that entire nephron. But most of tubular reabsorption, the biggest impact of tubular reabsorption takes place in the proximal convoluted tubule. So the good stuff is taken back. Water, glucose, ions, all the stuff your body wants. Most of it is reabsorbed. Electrolytes, vitamins, amino acids. 99% that's already been put in the nephron, in the filtrate, goes back into the blood. And most of it happens in the proximal convoluted tubule. That's what that stands for, PCT. And then we have the slide again to review. So this is the amount that's in the nephron after filtration in the glomerular capsule. This is the amount that's reabsorbed. 2 grams of protein. And 1.9 is taken back. All of the glucose is taken back. Okay, half of the urea. None of the creatinine. So that's more of a waste product. Urea is more of a waste product. Now, this image is essentially how urine becomes concentrated or dilute. We're going to not dig into the details here right now. But essentially this loop of Henle, it has the ability to concentrate urine. And urine is actually, or can be, 4 times more concentrated than blood plasma as far as ions are concerned. And there's going to be something called a concurrent multiplier that we'll talk about. So in your reading, make sure you don't focus on that, because that's not going to be something that we're going to focus on right now. Now, this is something interesting. You're essentially, this is called renal threshold. The nephron only has a certain ability to absorb a certain amount back into the blood from the nephron, and that's called the renal threshold. Only a certain amount can be reabsorbed. But if you have more in the nephron than can actually be reabsorbed, or if it's surpassed, it can't be reabsorbed fast enough, so it stays in the nephron. It has to be excreted in the urine. The best example, and the example that probably you can understand, is glucose. The renal threshold to reabsorb glucose from the nephron into the blood is normally about 180 to 200 milligrams per deciliter. If we have more glucose in the blood than normal, this renal threshold is going to be surpassed. So your blood, via reabsorption, it cannot absorb all that glucose. So normally, right here, normally we don't have glucose present in our urine. But if you have too much glucose in your blood to begin with, that renal threshold it goes over that renal threshold, you're going to have glucose in your blood. Tubular secretion. Now, we talked about how tubular reabsorption happens along the entire pathway of the nephron. So does tubular secretion, the third step. The movement of substances from the blood back into the nephron. It doesn't happen in the filtration membrane, and it mostly happens via active transport. The main thing here, why tubular secretion? Why are items going to go back into the nephron again? Controls pH. Controls pH. It can get rid of hydrogen ions, ammonia ions, other waste, urea. This is what it gets out. Hydrogen ions, potassium, ammonia, drugs like penicillin, alcohol, different things like that, out. And it often depends on just what the body needs to help maintain homeostasis. The pH is kind of a big deal. We don't want our body fluids to become too acidic or too basic, right? Alkalosis, acidosis. But so the kidneys, as well as a few other organs, are responsible for maintaining pH. Lungs eliminate carbon dioxide, which can adjust your pH in minutes. The kidneys eliminate hydrogen and ammonia ions to lower or to raise the pH. Bicarbonate, it holds on to, which actually raise the pH as well. That's a slower response though. And then your digestive system along with your skin also help with maintaining pH homeostasis. So the hormones involved in specifically helping to monitor ions like sodium, like potassium. One of those hormones is antidiuretic hormone, which is released from the posterior pituitary, which we talked about in the endocrine system chapter. So the brain picks up that the blood pressure is low, essentially. What part of the nephron does the antidiuretic hormone affect is the end of it, the distal convoluted tubule and the collecting ducts. And it actually causes these cells, the permeability of these principal cells right here, absorb more water. So move more water from the nephron into the blood, back into the body. So if it's absorbing more water, number one, your urine's going to be more dilute, more concentrated, and your blood volume is going to be